There is no sound. No wind rustles the canopy because the canopy has been erased. No bird calls pierce the air because the avian lineage, the dinosaurs that will one day conquer the sky, will not evolve for another 100 million years. There is no buzzing of insects in the underbrush because the underbrush has been chemically dismantled, and the insect class, historically the most resilient of all terrestrial life, has suffered its only mass extinction event in deep time. The date is 252 million years ago. The location is everywhere. You are standing on the shore of a dead ocean, the superocean known as Panthalassa. The water is lethally warm, approaching 40 degrees Celsius in the shallows, a temperature that denatures proteins and collapses metabolic functions in complex organisms. It smells wrong. The air carries the distinct, rotten egg stench of hydrogen sulfide. This is the olfactory signature of a biosphere in collapse. In the absence of oxygen, anaerobic bacteria have bloomed in the stagnant water, producing toxic sulfides that bubble up from the depths, poisoning the surface and stripping the ozone layer. The waves lap against black rock, but nothing lives in them. The reefs that once stretched for thousands of kilometers, built by rugose and tabulate corals, are white and silent. Their calcium carbonate skeletons are dissolving as the ocean acidifies, their architects extinct. Behind you, the land rises in brown and gray, folding toward a horizon that shimmers with heat haze. There is no green. The great forests of the Carboniferous and Permian periods, the vast Glossopteris flora, the seed ferns, the cordytes, are reduced to stumps and ash. The soil itself is dying. Without root systems to anchor it, the pedosphere is washing away, stripping the continents down to bedrock and choking the rivers with abiotic sediment. This is the morning after the end of the world. The Permian-Triassic extinction event, colloquially known as the Great Dying, has just concluded. It obliterated approximately 96% of all marine species and 70% of terrestrial vertebrate families. It was the closest multicellular life on Earth has ever come to total annihilation.
The primary driver of this catastrophe was not an asteroid impact, but a geological apocalypse originating from the Earth's own interior. In what is now Siberia, a mantle plume punched through the crust, creating the Siberian Trap's large igneous province. For roughly 1 million years, flood basalts erupted across an area the size of Western Europe. But lava alone did not kill the world, the volatiles did. The magma burned through vast subterranean deposits of coal and evaporites, releasing trillions of tons of carbon dioxide and methane into the atmosphere. The result was a hyperthermal event of terrifying speed and magnitude. Global temperatures spiked, triggering a runaway greenhouse effect. As the oceans absorbed the excess atmospheric carbon dioxide, they acidified, causing a collapse in the carbonate-silicate cycle. Organisms that built shells from calcium carbonate simply dissolved. Simultaneously, ocean circulation stagnated, leading to widespread anoxia. Oxygen levels in the atmosphere plummeted to roughly 15%, equivalent to the air at the summit of a tall mountain today, while hydrogen sulfide gas bathed the land. Life did not vanish in a single moment. It was dismantled in pulses over tens of thousands of years. The food webs collapsed from the bottom up. The primary producers died, the herbivores starved, and the predators turned on one another until the trophic pyramid disintegrated. And now the volcanism is quieting. The atmosphere is beginning to stabilize, though it remains toxic. The worst mass extinction in Earth's history has run its course. What remains is a disaster fauna, a simplified ecosystem dominated by bacteria, fungi, and a handful of opportunistic survivors. We see the scars of this event in the geological record. Paleontologists refer to the early Triassic as the coal gap. For nearly 10 million years following the extinction, no coal deposits formed anywhere on Earth. Coal requires peat, and peat requires forests. The forests were gone. Instead, we find the fungal spike. Stratigraphic layers from this period are abnormally rich in fungal spores, evidence of a world where the primary biological activity was the decomposition of the dead. The fungi were the temporary inheritors of the Earth, feasting on the decaying biomass of a planet that had essentially turned into a compost heap. Geography exacerbates the desolation. If you could view the planet from space, it would look alien. The familiar blue marble with its scattered continents does not exist. Instead, there is one massive landmass, Pangaea. Stretching from pole to pole, this supercontinent aggregates nearly all of Earth's crust. Its formation has profound climatic consequences. The interior of Pangaea, thousands of kilometers from the moderating influence of the ocean, is a hypercontinental desert. It is a zone of extreme continentality where temperatures swing wildly between scorching days and freezing nights. The climate is driven by mega monsoons, seasonal wind reversals of unprecedented scale. During the summer, the land heats up faster than the ocean, drawing in moisture-laden air that dumps torrential rains on the coasts while leaving the interior bone dry. During the winter, the flow reverses, drying out the continent completely. This is a world of extremes, hostile to the delicate equilibrium required for complex ecosystems to recover. Yet, life persists. In the shadows of this broken world, one vertebrate has risen to dominance. It is not a dinosaur. Dinosaurs do not yet exist. It is Lystrosaurus.
Lystrosaurus is a dicynodont, a two-dog-toothed therapsid, belonging to the lineage that will eventually give rise to mammals. It is roughly the size of a pig, with a barrel-shaped chest, stout limbs, and a face dominated by a beak and two downward-curving tusks. It is an unglamorous creature, yet in the early Triassic, it achieves a level of dominance that is statistically impossible. In the immediate aftermath of the Great Dying, Lystrosaurus accounts for up to 95% of all terrestrial vertebrates. This is the definition of a disaster taxon, an organism that thrives not because it is specialized, but because it is durable. Lystrosaurus survived where others perished, likely due to a combination of physiological plasticity and behavior. It was a burrower, a fossorial animal capable of digging underground to escape the lethal surface temperatures and the bathing ultraviolet radiation. Its barrel chest suggests huge loge, perhaps an adaptation to cope with the hypoxic, low-oxygen atmosphere. It was a generalist herbivore, capable of processing the tough, low-nutrient vegetation that survived the extinction. While the great Gorgonopsians, the saber-toothed apex predators of the Permian, suffocated and starved, Lystrosaurus dug in. It bottlenecked through the catastrophe and emerged into an empty world with no competitors and no predators. For millions of years, the terrestrial ecosystem was essentially a monoculture of these shovel-faced survivors. But Lystrosaurus is a relic of the old world, a placeholder. The Triassic period is beginning, and it will last for 50 million years. It is a time of reconstruction. The biosphere is damaged, the genetic diversity slashed to a fraction of its former glory. The recovery will be agonizingly slow. The coal gap proves that the complex forest ecosystems will take millions of years to return. The reefs will take even longer.
However, the evolutionary vacuum created by the Great Dying offers an unprecedented opportunity. With the established incumbents gone, the ecological stage is empty. The constraints that held back experimentation in the Paleozoic are lifted. In the riverbeds and coastal swamps, small populations of surviving reptiles are beginning to diversify. They are testing new body plans, new metabolisms, and new ways of moving. Among them are the archosaurs, the ruling reptiles. Currently, they are minor players, overshadowed by the ubiquitous herds of Lystrosaurs. But they possess anatomical innovations, advancements in respiration and locomotion that will soon allow them to challenge the mammal-line ancestors for control of the planet. For now, though, there is only the silence, the empty ocean, the brown hills under a hazy, high CO2 sky. The Triassic begins not with a bang, but with a long, slow exhale. The Earth is exhausted. The great experiment of the Paleozoic is over, and the Mesozoic has begun in the ashes. You are standing at the genesis of a new era, but it does not feel like a beginning. It feels like an ending that forgot to finish. The silence is immense, but somewhere in the cracked mud, something is breathing. The seed of the next 250 million years has been planted. 50 million years is a long time to wait for a forest, but the wait is finally ending. The brown, desiccated hills of the early Triassic are changing color. Along the river valleys and the coastal margins, the recovery is taking root. The flora that returns is different from the swampy giants of the Carboniferous.
those are gone forever. The new world belongs to the gymnosperms, the naked seed plants. Conifers like Voltsia anchor the soil with thick root systems, their needles coated in wax to retain moisture. Cycads, with their stout trunks and stiff fronds, colonize the nutrient-poor earth. Ginkgos line the waterways.
With the return of vegetation comes the return of complexity. The silence of the post-extinction world is broken by a new sound, stridulation. The Titanoptera have arrived. These are insect giants, orthopterans related to modern grasshoppers, but built on a scale that will never be seen again. Some species boast wingspans of 40 centimeters. They possess specialized ridges on their wings, organic instruments designed to produce sound. For the first time since the Great Dying, the air is vibrating with communication. The food web is rebuilding itself, layer by trophic layer. But the true revolution is happening in the vertebrates. The survivors are diversifying, and a new clade is rising to dominance, the archosaurs, the ruling reptiles. In the Middle Triassic, an evolutionary arms race begins, centered on a piece of anatomy that seems trivial, the ankle joint. The archosaurs split into two distinct lineages based on this biomechanics. One group develops a cruotarsal ankle, a complex peg and socket joint that allows for rotation. This design enables these animals to sprawl like a lizard, or stand upright and high walk when speed is required. These are the pseudosuchians, the false crocodiles.
The diversity of this lineage is staggering. In November 2025, paleontologists working in southern Brazil described a new species from this group, Tenured bellator. Unlike the lumbering giants, this animal was gracile and agile, a mid-sized predator that combined speed with defense. Its body was encased in osteoderms, bony plates embedded in the skin, providing armor without sacrificing mobility. It illustrates that the crocodile-line archosaurs were filling every available predatory niche, from the heavy infantry to the light skirmishers. They are joined by the adiosaurs, the heavily armored herbivores. Imagine a creature with the snout of a pig and the armor of an armadillo, built on the scale of a crocodile. Recent studies on Calyptosuchus, an adiosaur from the Chinle Formation, reveal a complex arrangement of interlocking plates that protected the animal from neck to tail. These were the tanks of the Triassic, grazing on ferns while the Rheasuchians prowled the perimeter. While the archosaurs conquer the day, the former rulers of the Permian, the synapsids, have been forced into the shadows. The cynodonts, the direct ancestors of mammals, cannot compete with the large, aggressive reptiles in the sunlight. To survive, they retreat into the nocturnal niche. This pressure drives a profound physiological shift. To function in the cool of the night, the cynodonts evolve endothermy. They become warm-blooded. But generating internal heat is metabolically expensive. It requires constant fuel. To make the math work, they shrink. They become small, insectivorous, and hyperactive. They develop fur for insulation to retain that precious heat. They evolve whiskers to navigate in the dark, and complex differentiated teeth to process food rapidly. The blueprint for the mammalian class is being drafted in the dark, driven by the necessity of avoiding the pseudosuchian gaze.
The Pseudosuchian dynasty seems unshakable. They are large, diverse, and entrenched. The early dinosaurs, by contrast, are marginal players. Small, bipedal scavengers like Eoraptor, darting through the underbrush, trying not to be eaten. They are rare, constituting less than 5% of the terrestrial fauna. Then, the weather changes. Approximately 234 million years ago, the planet experiences the Carnian pluvial episode. The trigger is the eruption of the Wrangellia Large Igneous Province, a massive volcanic event in what is now Western North America. The injection of carbon dioxide into the atmosphere causes global temperatures to spike, which in turn supercharges the hydrological cycle. For roughly 2 million years, it rains. This is not a standard monsoon, it is a climatic state shift. The arid red-bed deserts of Pangaea transform into humid basins. The xerophytic flora, plants adapted to drought, die out, replaced by lush, water-loving ferns and giant conifers. The greenhouse earth becomes a hothouse swamp. This shift is catastrophic for the pseudosuchians.
Their biology and ecosystems were tuned to aridity. As the environment becomes wetter and the vegetation changes, they falter. But the dinosaurs, for reasons we are still unraveling, thrive. Perhaps it is their respiratory system. Dinosaurs possess a flow-through lung system, similar to modern birds, which is far more efficient at extracting oxygen than the tidal lungs of mammals or crocodiles. In the hot, humid, and potentially hypoxic atmosphere of the Carnian, this is a decisive advantage. Perhaps it is their upright bipedal gait, which allows them to navigate the waterlogged substrates better than the heavy quadrupedal adiosaurs. Whatever the mechanism, the fossil record shows a dramatic turnover. This is the dinosaur diversification event. In the wake of the rains, dinosaur populations explode. They grow larger. They begin to radiate into the niches left vacant by the declining pseudosichians. We see this global spread in discoveries like Musanqua sanyatiensis, described in May 2024 from the shores of Lake Kariba in Zimbabwe. This animal is a sauropaudomorph, an early relative of the long-necked giants. Its presence in Africa, contemporaneous with similar species in South America, proves that dinosaurs were rapidly colonizing Pangaea, moving across the supercontinent as barriers fell. The boundaries of what constitutes a dinosaur are also being pushed back. In October 2024, the description of Gondwanax paraiensis from Brazil reignited the debate over the Silosaurids, a group of dinosaur-like reptiles. Gondwanax possesses 3 sacral vertebrae, a trait previously thought to be unique to true dinosaurs. This suggests that the dinosaur lineage may have originated even earlier than we thought, diversifying in the Middle Triassic, waiting for the trigger of the Carnian rains to unleash their potential. By the time the rain stops and the arid conditions return in the late Triassic, the world has changed. The pseudosutians are still present, still dangerous, but their absolute stranglehold is broken. The dinosaurs have ascended. The first giants of the dinosaur lineage appear. Plateosaurus, a prosauropod, reaches lengths of 8 meters and weights of up to 4 tons. It is the first time a dinosaur has achieved the status of a mega herbivore. They move in herds, their long necks allowing them to browse high into the canopy, their massive guts fermenting the tough vegetation. They are the heralds of the Jurassic titans to come. The balance of power has shifted. The ankle joint that favored stability and power is losing ground to the ankle joint that favors speed and efficiency. The Triassic began with a lonely Lystrosaurus wandering a dead world. It enters its final act with a vibrant, competitive, and deadly ecosystem. The pseudosutians are the kings of the past. The cynodons are the ghosts of the night. But the dinosaurs are the future, and they are just getting started. While the land is a battlefield of ankles and metabolisms, the ocean is undergoing a transformation of scale. The reptiles have returned to the sea, and they have done so with terrifying efficiency. The ichthyosaurs, initially lizard-like paddlers, have evolved into hydrodynamic marvels. They have converged on the body plan of the tuna and the dolphin, streamlined fusiform bodies, dorsal fins for stability, and lunate tails for high-speed propulsion. They are viviparous, giving birth to live young, severing their last tie to the land. By the late Triassic, they reach sizes that defy comprehension. Recent discoveries, such as Ichthyotitan severnensis, described in April 2024, reveal animals approaching 25 meters in length, rivaling the modern blue whale. These are not filter feeders, but apex predators patrolling the Panthalassic Ocean. The discovery of this giant was a triumph of citizen science. The first fragments were spotted by 11-year-old Ruby Reynolds on a Somerset beach. These bones tell us that the Triassic oceans were capable of supporting massive caloric demands. The marine food web, so utterly destroyed by the Great Dying, has not only recovered, but has scaled up to support the largest marine reptiles in Earth's history. Above them, the conquest extends to the sky. The pterosaurs have achieved powered flight, the first vertebrates to do so. They evolve a wing distinct from birds or bats, formed by a membrane of skin and muscle stretched from an elongated fourth finger. Their bones are hollow, their respiratory systems pneumatic. They are not merely gliding, they are actively hunting, exploiting an aerial niche previously held only by insects. Eudomorphodon, with its complex multi-cusped teeth, snatches fish from the Tethys Sea, proving that the archosaurs have now colonized land, sea, and air.
On land, the first giants appear. The sauropodomorphs, ancestors of the long-necked titans, evolved from small bipeds into multi-ton herbivores like Plateosaurus. They are the first evidence that dinosaurs are moving toward gigantism, utilizing gut fermentation to process vast quantities of plant matter. But Pangaea is restless. The supercontinent is beginning to unzip. Deep crustal rifts are forming, heralding the birth of the Atlantic Ocean. This rifting triggers the Central Atlantic Magmatic Province (CAMP) event, roughly 201 million years ago. It is another flood basalt eruption, similar to the one that started the Triassic, though slightly less apocalyptic. Yet the effects are devastating. The Triassic-Jurassic extinction event eliminates 76% of species. The selective nature of this extinction is baffling. The Pseudoseuchians, the dominant Rauisuchians, the armored Aotaurus, the Phytosaurs are wiped out almost entirely, leaving only the lineage that will become modern crocodiles. The dinosaurs, however, survive unscathed. Why? Perhaps their rapid growth rates allowed populations to recover faster. Perhaps their primitive insulation, protofeathers, protected them from the volcanic winters that alternated with greenhouse warming. Perhaps their superior locomotion allowed them to migrate across a fragmented landscape. We do not know for certain, but the result is absolute. The competition is dead. The Pseudoseuchian stranglehold is broken. The Triassic began in silence and ends in fire, but it has served its purpose. It was the crucible. The ecosystems have been rebuilt, the body plans tested, the weak filtered out. As the volcanic ash settles and the Jurassic dawn breaks, the survivors step out of the shadows. The era of the experiment is over. The age of the dinosaur has begun.
The night is quiet now. The volcanoes have stopped. The extinctions have ended. The survivors are resting, waiting for the Jurassic sun to rise on a world that belongs to them. You have traveled far, from the silence after the great dying to the fire of the camp eruptions, from the empty shores of Pangaea to the crowded forests of the late Triassic, from Lystrosaurus walking through ash to Plateosaurus browsing on conifers, from the first nothosaur slipping into the water to the first pterosaur taking to the sky. 50 million years of recovery, 50 million years of evolution, 50 million years of life finding ways to fill every available space, to exploit every available resource, to become something new. The Triassic is a story of resilience. Life was nearly destroyed, and it came back. The world was broken, and it healed. The niches were empty, and they filled. The dinosaurs did not know they were inheriting the Earth. They were just surviving, generation by generation, the way every living thing survives. The Rauisuchians did not know their dynasty was ending. The Cynodonts did not know their patience would eventually be rewarded. None of them knew anything. They lived and died, and left bones in the rock for us to find. The bones tell the story. The rocks remember what the animals could not. Rest now. The Triassic is behind you. The Jurassic is ahead. A world of giants, a world of wonders, a world that grew from the seeds the Triassic planted. That is another story, another night, another journey through deep time. For now, the world is quiet. The great dying is over. The long recovery is complete. The dinosaurs are dreaming of a future they cannot imagine, and so can you. The Triassic will still be there in the morning. The fossils will still be waiting in the rock. The story will still be unfolding, one discovery at a time, one bone at a time, one patient scientist at a time.